In this video, we look at shading to solve the set operations with three sets. This is the standard way of drawing a Venn diagram with three sets. Here we have the universal set, and the set A, B, and C. These three circles here, and you'll notice, you'll be familiar with the Venn diagram for two sets, so A and B. You need to just include this third set across the bottom. And when you draw a Venn diagram with three sets, you should have these 8 regions. And again, I just put a number in here so that there's a 1, 2, 4, and 5. Those are A. 2, 3, 5, 6. Those are in B. And 4, 5, 6, and 7. Those are in C. But I want you to think about something here. This region right there, this is the overlap of A and B, so 2 and 5 are in A intersect B. In the overlap between A and C, you have 4 and 5, so 4 and 5 are in the intersection of A and C. And then 5 and 6, those are in the intersection of B and C. Now what's going on right here? You'll notice that all three sets contain 5. So 1, 3, and 7 are in just one set. 2, 5, 4, and 6, those are in 2 sets, but 5 is actually also in all 3 sets. And then 8 is outside. So let's think about this. I've numbered these. After I wrote them down, I realized it makes sense to do this one first. If we're looking for A intersect B intersect C, A intersect B intersect C, we're looking for that's just this piece right here. That would be just 5 right there in the middle of the Venn diagram. If we had A intersect B union, A intersect C union, B intersect C. So this is the union of these 3 intersections. So A intersect B with A intersect C with B intersect C. So just putting all of these together, if we wanted to shade, we could do that because it's a union. Just go ahead and shade each part, and the union brings all 3 parts together. A intersect B is going to result in this part right there. That's A intersect B. A intersect C is this part right here, and B intersect C is this part right here. Okay, so since we're taking the union, the elements that are included in all of that would be 2, 4, 5, and 6. I don't need a yeah, I do. Sorry. 2, 4, 5, and 6 are the union of each of those intersections. You'll notice that 5 looks pretty dark because it actually was shaded. That region there was shaded 3 times. It's a part of each one of these 3 intersections, but it still just shows up once because this is the intersection of all 3 of those. Now the union of A, B, and C, that's just going to be anything that's in A or B or C, 2 of them or all 3 of them, like this.
Okay, so in that case, the union is 1, 2, 3, 4, 5, 6, 7. The only thing that's not a part of the union is 8. Okay, so if we did the complement of A union B union C, if we took the complement of all of this, then that would be 8. All right. Second one down here. Again, standard Venn diagram with 3 sets. After I wrote these down, I think it makes more sense to do this
second one first, the B union C, and then we're going to take the intersection of that with A. Same thing with order of operations, PEMDAS. You do the parentheses, what's inside the parentheses first. So B union C intersect A. So we're going to shade these two using a different pattern, and then whatever region has both patterns of shading will be a part of the intersection. B union C. B union C is anything that's in B or C or both. So that's going to be this. That's B union C, and then intersecting for A this way.
Shading, if you guys want to do, if you want to shade with daisies and hearts, that's entirely up to you, but just try to keep it simple. So the intersection of these two, hopefully that's really clear. The intersection is this little shape right here, and that would be 2, 5, and 4. 2, 4, and 5 is the region of A, B, and C that's included in this. So go ahead and write that down. 2, 4, 5. And then A union B, let's see if we can talk ourselves through this. A union B is, you know that what that is. A union B is 1, 2, 3, 4, 5, 6. That's just the union of A and B together. But this part says and outside of C. So what part of A union B is also outside of C? 1, 2, 3, 4, 5, 6 are in the union, but 4, 5, and 6 are down here in C. So the part of A union B that's also and outside of C, that's just going to be 1, 2, and 3. Okay, now if we were doing this, if we had its own Venn diagram to shade, we would shade this one way, shade this another way, and then look for the part that was shaded both. But I think you can reason that it's going to be 1, 2, and 3 just by what we've learned so far. Okay, and finally, down here we have a symmetric difference. Remember what this is all about? We're trying to figure out the part that's in the union but not in the intersection. So if we look for A union B, you guys know that that's one of our standard operators, so we should know right away what that's going to look like. A union B is that part right there. And then C, let me just use something really different here. So I shaded A union B that way, shaded C that way. So what this says is I'm looking for all of those elements of the Venn diagram that are in the union. So they're in the union of these two parts. So the union of the first part, which is A union B, but they're also in C, but not both. So I'm looking for anything shaded this way and shaded this way, but not shaded twice, because that would mean it's in the overlap, it's in the intersection. Okay, so not shaded twice, that you can see really clearly, that's just right there. So 1, 2, 3, and 7 are just those elements that are only in one of the, in a region that's shaded just once. 1, 2, 3, because that's a part of A union B. 7, that's a part of C. 4, 5, and 6, that's a part of both. Leave that out. The symmetric difference doesn't want the intersection, it just wants what's in one or the other, but not both. Okay? All right, hopefully that sets the stage so that you'll be able to do some of the practice problems, some of the homework problems that have been assigned out of